In the previous video, we talked about the continuous and digital signal, and we say that continuous is in fact analog, and analog itself in terms of a real-world model, and often we want to model things in terms of the digital world, correct? And how do we model things? Normally when we model things, we have to change the real-world system in terms of a certain differential equation. Alright, the real-world system is often denoted by certain, like, if you talk about mass, if the mass is rotating, we are talking about a torque with a summation T is equals to I, the moment of area times the angular acceleration. If the mass is moving, x, y, or lateral, I would say, then you're talking about summation of forces is equals to mass times the acceleration. Alright, it's simple. It's all this stuff. If it's temperature, then it's in terms of another certain temperature equation or conservation of law. But anyway, as you know, as we can see now, this is the differential equations that we're talking about. And how do we solve differential equations is by four methods. Alright, and each four methods have individually gives us different information on the answers itself. Alright, the first one I'll go through is actually this one. Solve differential to get the function y equals to xt. If you remember the first case, second case, third case, alright, or in other words, ae kt plus b kt, the k itself gives you a certain understanding of how oscillatory this the signal will be and things like that. But in more details, it will not give you any information. So the amount of information over here is not very adequate enough if you want to go into details. But if you just want to solve for it, actually this will suffice. So the method of applications, it all depends on the method of information that you really want. Alright, the second method to solve is actually to Laplace transform, and you solve for the dE using a transfer function. Alright, if you remember, Laplace transform is in terms of the transfer function, and also to help us find stability of the system and to model the system. Alright, the next one is convert to state space, where you convert higher order to only first order system. Alright, and then it's also talking about stability. The last one is factorization to a lower order system. It's very similar to state space, but the amount of information is really different. So you may have d2y dt square, alright, is equals to y double dot t, alright, and therefore I can actually state that dy dt is equals to a. Alright, if I were to differentiate a, then I'll have d2y dt square. Or in other words, I would say that this a dot is actually dA dt. Okay? And therefore this can be simply written as that. I can re-represent the whole system as another alphabet. Okay, or I can say a as maybe a is equals to x1. Right? A dot is equals to x1 dot. Sorry, is equals to x1 dot, and we can call it as x2. Alright, so as you can see, this is very similar to state space, but in terms of different stuff, we will not talk about it. Okay, and therefore in this video we'll more focus on the Laplace transform. Okay, because everything when we model things, we are going to model in terms of the transfer function, correct, to be more detailed. And therefore we're gonna do Laplace transform in a more different way. Alright, we call this the inverse Laplace. Alright, Laplace transform of the differential equation. Alright, I believe you already know, I will assume that you already know this inverse Laplace of the differential equation, but I just want to explicitly define in terms of this one. Alright, we are now going to solve in terms of y dot t. Alright, how do we solve? The first step you're gonna do is to set up the transfer function, alright, which is equals to the forward loop. The forward loop is actually 1 over s going in this direction, divided by the feedback. Alright, 1 plus the feedback. Alright, 1 plus or minus, it all depends on this. If it's a plus, then the feedback is actually a minus. If it's a minus, then the feedback is actually a plus. Okay, I don't go into details, but just take it as it is. Alright, never mind, I'll explain it quickly. Okay, So for example, if I send an input of 5, alright, and I foresee that I want my output to be 5 also, but however the feedback tell me that I have an increase of 2. Okay, I have increase of 2, which is y plus over here, and therefore the next signal that I'm going to send is send 3. Alright, I'm not going to send 5, and therefore 3, because this transfer function will give us a +2 system, and therefore at the end you have 0 over here and we have a 5. I think you get what I mean, right? So it's like the feedback system tells you whether are you more than what you would want it to be. Alright, if you want it to be this amount, and if it feedbacks more amount, this means that you're gonna decrease the input, and this is why I put minus over here. So this is the opposite side. If it's a plus, then we put minus. If it's a minus, we put plus. If you don't understand anything, you'll just click back a few minutes ago while I've just said, and then you'll just repeat and repeat until I think it should be fine. Okay, and therefore if I were to multiply s by over s, it's simply 1, meaning that I'm gonna rearrange this thing, and therefore I would have 1 over s minus plus p. Okay, which is equals to the output. The output is over here, and over the input, where the input is over here. Okay, now I'm gonna rearrange. I bring this us up, I bring this I bring this thing up there. Alright, what I will have is this one. Okay, so I'm just multiplying this one into both of them. Okay, and therefore I have this. Okay, I'm simply bringing this thing, okay, up to the side, and then multiply in the ys. So therefore I have sys and I have a pys over here. Okay, I hope this is pretty much clear. Therefore now comes the differential equation, alright, the Laplace differential equation. If you know, okay, so y dot t is equals to, if you Laplace it, alright, is equals to s y s, alright, minus y0. Alright, if it's a y dot t is equals to s square ys minus y prime 0 minus s y prime 0 minus minus y0. If it's yt, then it is simply ys. That's all. I will just explicitly say that this is y, capital Y. Right, these are all capital Y. And in fact, this is also capital Y. Okay, and therefore what can you, and the next thing I want to let you know is that the initial condition for y0 is equals to 0, and this one is equals to 0. This is the initial condition, and therefore we can say that this is 0, this is 0, alright, and this is 0. Okay, because since y prime 0 is 0, y0 is 0, hope you get what I mean, and therefore the end result is that this is it. Y double dot t is simply s square ys, y dot t is simply s ys, yt is simply ys. So we're gonna exploit this understanding and apply it into our dude over here. Alright, and therefore us is simply ut. Alright, because ys is simply yt. Therefore, if it's in terms of u, then it's just ut. Okay, sys in this case, you have an s in front of a ys. Then what we are talking about is a first differential equation. Alright, same thing. So I'm just simply sub it in over here, y dot t minus plus, and then p. Alright, ys is simply yt. Okay, this is the definition, and in fact this is also y. Okay, sorry. And therefore if I were to rearrange, alright, in terms of y dot t, I would have pyt, alright, me see. Okay, so I'm gonna bring this to the other side. Okay, and therefore it's ut plus minus pyt. Okay, and this is it. This is to solve for the this portion over here. Okay. Okay, now instead of having the p as the feedback loop, alright, I place p with 1 over s at the forward loop. Okay, so as a practice, I'll just go in a fast way. Alright, so set up the transfer function. The forward loop is simply p over s, 1 plus feedback loop is also p over s, is equals to p s plus p. Okay, the feedback is simply this whole line. Okay, this is why I still say that it's still p over s. Okay, if you don't know what I mean. And then I multiply s over here. This is why I have this one, because the s will cancel out with this s, the s will cancel out with this s, and then multiply with s. Anyway, and then this equals to the output over the input. And I bring this up, what I would have is this one, okay, minus plus. Actually forget to write that, minus plus. It all depends on your this form. Okay, and therefore we know that sys from the previous definitions. If you forget, maybe I just paste this too, because I have no double integration differentiation right now. Alright, I'll just do this. We know that sys is simply y dot t, and then we can just write as y dot t minus plus py t, because ys is simply yt. Okay, and then we know that us is simply ut, and therefore I have put. And therefore, if I were to rewrite in terms of y dot t, now I would have put plus minus pyt. Alright, and this is it for this portion over here. Okay, so as you can see, the trend is starting to get a little different. The p is over here right now at the feedback. Now the p is over here. Now in the last scenario is that I set the 1 over s as the feedback also. Okay, so similarly now I will still do the same thing. Alright, set up the transfer function. Okay, this is a practice, so at least you can download into you right now. So when I set up the transfer function, the forward loop, be very careful. Now the forward loop is empty, it's just 1. Alright, and then 1 minus plus. Alright, this is the feedback, is plus minus. Alright, and then I have p over s. Alright, this is going in this direction. And therefore, if I were to multiply or rearrange, I could have s plus p is equals to ys us. I bring this up, what I would have is sus is equals to sys plus pys. Okay, and then now same thing, I'm gonna paste this definitions over here. Alright, sus is very similar to sys. Alright, sys is y dot t. If it's sus, then it's simply x dot t. That's all. Okay, it's just a definition. Okay, sys is y dot t, and therefore y dot t plus pyt. Right, ys is simply yt. And I rearrange again. Alright, I actually forget the minus plus sign. Yt, alright, this is it. I just simply bring this over the side. And then why you may wonder why is this minus plus, and then if I were to bring to the other side it's plus minus. Because if you were to bring, for example, if you were to bring pyt over this side, it simply becomes plus, right? And therefore, if this one become plus, then the bottom one will become minus. Alright, it's just a sign convention. Okay, and therefore what we have is x dot t plus minus pyt. Okay, now why do we interested in y dot t and yt, and why do we want to set up this equation, and why do I want to go into all these details and then solve for things? Alright, this is the question that you may ask. Okay, if you take a look, transfer function, we are always setting up the transfer function. Okay, and the transfer function itself is simply this one. Alright, the input versus the output, or in other words, ys over us is equals to gs. Alright, now this is particularly very useful is when you can only measure your output, alright, and the rest, or perhaps you don't know the transfer function. Alright, you don't know the transfer function, you want to like so-called reverse engineer. Right, you want to reverse engineer certain stuff. You know the output, and you can also apply your own input. Okay, so in this case, if I want to apply my own input, I would apply it as 1. How do I, and at what situation the Laplace transform or us is 1? At impulse, right? An impulse function in the Laplace domain is simply equals to 1. Alright, I believe that you already remember that, so I'm not going to go through in details. And therefore, if this is 1, then I can simply say that ys is equals to gs, because us is simply 1. Ys divided by 1 is simply ys. So we can say that the output itself is the same as the transfer function. Okay, but this doesn't explain, right? Why this also still doesn't explain why do I want to do y dot t and yt. Correct? We know that the input is 1. Right? For example, if our output is 5, we measure that it is 5, perhaps maybe 5 meter. Okay, in terms of yt. Okay, I will not ask you to differentiate lah. Okay, but with this information, alright, or with this information 5 meter, this is your objective right now. Alright, you run a series of measurement, alright, 5 meter, 10 meter, 15 meter. Right, you have a data of ys. Okay, and therefore you can just design any transfer function. You can design any artipalan one. You can design this one. You can design this one. You can design this one. You can design all whatever you want. Happy can already, but ensure that the end result of the data that you measure is in terms of all these intervals. Alright, all the measurements are all this. Alright, if ensuring that all this output that you have measure, alright, from a engineered, alright, I have an engineered transfer function over here. Alright, if I have this transfer function that comes out a same amount of data that is same as my original measurement that I measure, then I can say that I have finally found the correct ingredient to simulate my output, and I can create whatever I want already. Alright, and therefore y dot t and yt is very important. Alright, because yt is in fact the output. Alright, it's coming to the end. It's over here actually, or perhaps over here. Over here can be yt, over here is yt, over here is yt also. Okay, it's the output. Alright, and over here is when the input interacts with the feedback. You remember the feedback tells you whether do you want to add more or do you want to minus more. Alright, so the input itself will straight away feedback to tell you that this thing gonna change. Right, this output, alright, in terms of this input, correct? This input with a certain 1 of s, alright, is gonna give you a output. So therefore you know that from here, if our input is 1, as we said earlier, if this is 1, then we know that the new feedback system is dependent of a certain constant p, okay, with a yt over here. This is your output, your own output, your initial output. Alright, and from there then you can calculate and things like that. Alright, so I'll not go into details. I know that this sounds very abstract, but the key in mind is that you want to model a transfer function based on your output only if you want to model that, because in the real world a lot of things is in terms of the output. So you're gonna measure a list of data of the output, and then you try to model in terms of a certain transfer function yourself, and try to, when you run your analysis for the transfer function, ensure that the data correspond to the one that you measured. If that's the case, then you have aced your prize. And this is the thing that I want to convey for the Laplace transform. If you still remember back, this is the solution. I mean, this is the way or the reason behind why do we use control. And I shall see you in the next video.